Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. The subject of this lecture is cyclic groups and order of elements. Let me tell you the context and the plan for this lecture. A group is a non-empty set together with one operation, a binary operation, and it has four properties. The operation is closed, it's associative, there's an identity, and there are inverses. I've had videos on definition of a group, and if you're not familiar with that, you should be looking at those first. In this lecture, I'm going to give you the notation for exponentiation in groups, and then we talk about the smallest subgroup group that contains a certain element. That will lead us to talk about cyclic group. We'll prove a theorem on finite cyclic groups because finite cyclic groups are actually particularly easy to work with and important to know about. We will talk about what the order of an element is, and we will prove an important theorem that says that if you take an element, raise it to a power, and you get identity, then the order of the element must divide that power. What are the prerequisites for this lecture? You should know what a group is, although I did tell you what it is, but I have videos that go into more detail. And you should know something about what the abstract algebra project is. What are we trying to do? And I have videos on what abstract algebra is as well. But more importantly, whenever we want to work with groups, you need to know some examples of groups. In terms of the theorems that I prove, the examples really don't matter because I'm proving things in general for all groups. And so my arguments should be true regardless of any examples. But it's very hard to build intuition or understand what's going on without looking at examples. For example, D8, the symmetries of a square. There are 8 of them. R0, that's a 0-degree rotation. R90, that's 90-degree rotation counterclockwise. R180, R270, and then there are 4 reflections. H is the horizontal reflection, V is the vertical reflection, and there are 2 diagonal reflections. I have a whole video on D8. It's an important video to become familiar with what a group is and how to deal with D8. D8 is an example that we look at often whenever we do group theory. So another way to write D8 is in terms of generators and relations. So instead of R90, the 90-degree rotation counterclockwise, we put A, and instead of H, the horizontal reflection, we put B, and then D8 is generated by A and B. That means that all the words you can write from A and B are going to give you all those 8 symmetries, except that you have to know that there are 3 relations. A to the 4th, if you do a rotation 4 times, you get identity. B squared is identity. BA is A cubed B. If you don't know what I'm talking about, please go watch the video on D8. Another example is the symmetric group of degree n. The symmetric group is the permutations of n objects, or the set of one-to-one onto functions from n objects to themselves. We will use the cycle notation for elements of Sn. I have 2 videos on permutation groups and on the cycle notation for the symmetric group. We will also be talking about 2 abelian groups. Z mod n Z, integers mod n with addition, and the groups of units of that with multiplication. I have 1 video for each one of those groups. Finally, GLNP is the group of invertible n by n matrices with entries in Z mod PZ, where P is a prime number, and that's an important example to know as well. Again, for each of these examples, I have videos that go in much more detail. This should not be your first encounter with them. Let's start with the exponential notation. So you walk in a group, you pick your favorite element, and you pick a positive integer. A to the n just means A times A times A times A n times. When I say times, I mean use the operation of the group. The operation in the group might be addition, in which case this becomes A plus A plus A plus A. A to the 0 is always going to denote identity. And if I have A to a negative integer, that means A inverse to the positive power. A to the negative 5 means A inverse multiplied by itself 5 times. Let me repeat myself. A to the n means multiply A by itself n times. A to 0 is identity, and A to the minus n is A to the minus 1 to the n. Here's an example. Well, let's look at the symmetric group of degree 5. So that is permutations of 5 objects. Here's one element, 1, 3, 4, 2, 5, written in cycle notation. 1 goes to 3, 3 goes to 4, 4 goes to 1, and 2 and 5 are switched. If you want to find A squared, what does that mean? It means that you multiply this guy by itself, and you can multiply it without looking at the diagram here, and you'll get 1, 4, 3, or you can think about it. The 2 and 5 were switched. If you switch them twice, 2 stays put, 5 stays put, and if you do twice, 1 goes to 4, 4 goes to 3, and 3 goes to 1. And so we get 1, 4, 3. This is the cycle notation, and implicit is that the 2 and 5 are fixed. A cubed is doing A 3 times, or doing A squared times A, and you get 2, 5. Or you can think of it in terms of what this is. If you do this 3 times, the 1, 3, 4, that 3 cycle becomes identity. 1 goes to 1, 3 goes to 3, 4 goes to 4. And if you switch the place of 2 and 5 3 times, then that's the same as switching them once. You get the cycle 2, 5. A to the minus 1, that's doing things in reverse. So 1 goes to 4, 4 goes to 3, 3 goes to 1, and the place of 2 and 5 are switched. And A to the minus 2 means you take a minus 1 and multiply it twice. I urge you to do some of these multiplications to make sure that we are on the same page. Exponentiation follows some familiar rules. If A is an element of a group and you have two integers, positive, negative, or 0, then a to the m times a to the n is a to the m plus n. This is obvious if m and n are both positive. A to the m is ma's and a to the n is na's. And so if you put them together, you get m plus na's. But this also works with negative integers. All you have to do is make different cases. If m is negative, for example, a to the m means a inverse m times, and a to the n means, if n is positive, a n times. The inverses cancel the a's and you get a to the n plus m, remembering that m is negative. An inverse is a to the negative n. This is a claim that a to the negative n is making. It's making the claim that I am an inverse. I am the inverse of a to the n. How do you check such a claim? You take a to the minus n multiplied by a to the n, and you get identity, and therefore this claim is true. And a to the m to the nth power is a to the mn. Why? Because a to the m to the nth power means you take a to the m and multiply it by itself n times. The guiding question for this next little section is that you walk into a group, you find your favorite element, you say hello. Inside this group, what other elements do I need to gather together with A to make a group inside that bigger group? A small group within a bigger group is called the subgroup of the bigger group. So what elements do I need? What's the smallest subset of G that contains A? And it's itself a group. And this will be the subgroup of G containing A. Of course, you need identity, you need A inverse, but you need other things. You need A times A, and you need the inverse of that. You need A cubed times the inverse of that, and so forth. So you need A to all powers. That is a group. In fact, it's an abelian group. Abelian means that it's commutative. It follows the axioms of a group. It's closed. If you take two of these powers and multiply them, you get another one. Have an identity. It's associative because the original group was associative, and this inherits associativity from the original group. And we have inverses. This is an abelian group, and this is the smallest subset of G that contains A and is itself a group. An example, start with the group of non-zero rational numbers under multiplication. This is a group because it's closed. If you take two non-zero rational numbers and multiply them, you never will get 0 and you will get a rational number. And it's associative because multiplication of numbers is associative. The identity is 1. When you multiply it by other things, nothing happens. And the inverse of 2 is 1/2, and both are rational numbers, and so forth. So this is a group. What is the smallest subgroup of G that contains 1/2? What is the group that contains 1/2 that's sitting inside G? You need the identity, that's 1. You need A itself, you need its inverse, which is 2. Then you need A squared and its inverse, and so on. That will be all the elements of the form 2 to the n when n is an integer, positive, negative, or 0. That's a subgroup. It's an abelian group and a subgroup of G. Now we're going to define what we mean by a cyclic group. If you have a group and assume that you have this very special element in G, such that that smallest subgroup of G that contains A in it, that ends up being all of G. When you look at all powers of A, identity A inverse, A squared, A minus 2, and so forth, you actually get everything in G. Then in that case, G is called a cyclic group. And A is a generator of G. This A generates G, and we write pointy brackets A. But I'm never going to say pointy brackets. I'm going to say G is generated by A. A cyclic group is one that there is some element that if you look at the powers of that element, you get every element of the group. D8 is not a cyclic group. If you start with one of the rotations, you only get rotations. And if you take a reflection and keep doing it, well, you only get identity and that reflection. But inside D8, there are a lot of cyclic groups. For example, what is the subgroup generated by R90? That's R0, R90, R180, and R270. Using A as standing for R90, then it's A squared, and A cubed. This is the cyclic group inside D8. D8 is not cyclic, but it has a subgroup that is cyclic. In fact, it has many. The subgroup generated by H is just R0 and H being the horizontal reflection with our other notation for D8, note H by B. What about Z mod n Z? Integers mod n with addition. Whenever we write Z mod n Z and we're talking about it as a group, we're implicitly assuming that operation is addition, because with multiplication, even though we can do multiplication mod n, we do not get a group. If you look at Z mod 5Z, for example, the elements are 0, 1, 2, 3, 4, and I'm claiming that's a cyclic group. Why is that? What's the subgroup generated by 1? Start with 1, then you need 1 plus 1, that's 2. You also need the negatives, but if I just add things together, I will get all the elements. I will get all of 0, 1, 2, 3, 4. So 1 itself generates the whole group, and so that makes Z mod 5Z a cyclic group. Now, a generator doesn't have to be unique. In this group, for example, 1, 2, 3, and 4 all generate Z mod 5Z. 0 does not, because if you keep adding 0 to itself, you just get 0. But all the other ones do. For example, start with 4, you get 4, then you get 4 plus 4, which is 3. 4 plus 4 plus 4 is 2, and then 4 4s added together give you 1, and 5 of them added together give you 0. Remember that we're doing addition mod n. We are adding and then finding the remainder when divided by n. Same thing works for Z mod NZ. It's always generated by 1, because if you keep adding 1, well, of course, you will get all of the elements of that Z mod NZ, and so it's a cyclic group. It's not true that all non-zero elements are always generators. That will be true if n is a prime, but not otherwise. But the point is that all Z mod NZs are cyclic groups, and they're generated by 1. One other example is the group of units of Z mod 5Z, which we write as Z mod 5Z with the times on top. Z mod 5Z with addition is a group, but Z mod 5Z with multiplication modulo n is not a group, because not everything has an inverse. But if you take the invertible elements, which are called units, then you get what's called the group of units of Z mod 5Z, and that has 4 of the 5 elements of Z mod 5Z. It has 1, 2, 3, 4. All of those have inverses, multiplicative inverses, but 0 does not. That is a group. The operation is multiplication modulo 5. Is this a cyclic group? You might start with 4. Does 4 generate this? But if you look at powers of 4, you see that 4 squared, 4 times 4, well, it's 16 in our world, but if you do modulo 5, you get 1. 4 squared is already the identity. The identity of this group is 1. And if you look at any other powers, you either get 1 or 4. Well, if you look at inverses, the inverse of 4 is 4. The inverse of 1 is 1. This is already a group. 1 and 4 is a group, and it's not the whole group. So 4 did not generate this group of units. However, if you look at the group generated by 3, and if you look at its powers, 3 squared is 4, 3 cubed is 2, and 3 to the 4th is 1. And that's everything. 3 does generate the group of units of Z mod 5Z, and so this group of units is actually cyclic. If we look at 2 as a possible generator, we see that that also generates this group, and 1, which is the identity, never generates a group other than a group of size 1. The group of units of Z mod 5Z is a cyclic group of order 4. It has 4 elements, and it has 2 generators. 2 and 3 are its generators. I want to say something about additive and multiplicative notation. This is a slight tangent here. With groups, we always are talking about multiplication as the operation. The operation could be called anything, but our go-to word for talking about operation of a group is multiplication. However, if you have an abelian group, you could use either the multiplicative or the additive notations. Additive notation means that you use plus instead of the times or instead of the operation. We definitely use that when we're talking about Z mod NZ with addition, because the operation is addition. It's weird to then use multiplication when we really mean addition. For other abelian groups, we could use the multiplicative or the additive notation. Here's a little dictionary. In an abelian group, you might write AB as A plus B. The identity, if you write in the multiplicative notation, is 1. In additive notation, it would be 0. A to the 0 is identity. In additive notation, is 0 times A. That's 0. A inverse corresponds to minus A. The associative law, for example, will be written differently in both notations. And the one that maybe is more confusing is A to the n is the same as NA. A to the n is exponentiation, and NA is the same thing if you use the additive notation. If G is a cyclic group and A is a generator for G, then according to definition, we have to look at E, A inverse, A squared, A minus 2, and so on forever to find out what G is. And in fact, if G is an infinite group, this might take forever. However, if G is finite, we can do much better. We don't have to actually look at all these elements. There's a much more streamlined version. That's our next theorem. And this theorem has content and is important. Let's say you have a finite cyclic group. Then the fact is that there will be a positive positive integer k such that a to the k is e. That's one fact, that if you start with a and keep multiplying it by itself, you will get e automatically. Secondly, if you then take m to be the smallest positive integer where a to the m is e, then the order of g, the number of elements in this group, is m. If you start with a and keep multiplying it by itself, and the first time you get identity, see what the exponent was, that exponent is the size of your group. Moreover, if you just start with a squared, and so forth, as soon as you get to e, you've got your whole group. You don't have to worry about inverses. The inverses will automatically be there. I'm going to prove that. I'm in a finite cyclic group. The first thing I'm going to claim is that if you take a and repeat it, you get identity. There's a positive integer such that a to the k is e. Why would that be? Consider e and all the powers of a. This is an infinite list of symbols. It's not an infinite set because there might be repeats, but it's an infinite list of symbols. But g was finite, so there must have been repeats. And so a to the t and a to the s must be the same for t greater than s, and s is some integer greater or equal to 0. A to the minus s is the inverse of a to the s. If you multiply that on both sides, you get a to the t times a to the minus s is e. And that says that a to the t minus s is e. Let k be t minus s. Because t is greater than s, k is positive. And now we have that a to the k is e. So if you start with a and just keep multiplying by itself, you will eventually get e. And this is true for any element in any finite group. Because even if the group is not cyclic, that element generates a cyclic subgroup. And we know that there is positive integer k such that a to the k is e. And in fact, there will be many such k's. But pick the smallest positive integer and call it m. Consider this claimant to the throne. This set of elements claims to be all of g. We want to show that this is g and it has m distinct elements. Could it be that there's repeats in here? If ai was equal to aj for I greater than j, then that would mean a to the I minus j is e. You get that by multiplying both sides by the inverse of a to the j, which is a to the minus j. So you get a to the I minus j equals e. But I minus j is less than m. But m was supposed to be the smallest positive integer, where a to m was e. And now a to the I minus j is also e. And that will be a contradiction. So there's no repeats and the list has m elements. I've got a list with m elements, but does that include every element? I'm calling this the short list. This a squared, a to the m being e. So you start with a and just keep going until you get to identity, and you stop. You'd never worry about inverses. Could this have every element of g? G was generated by a, so elements of g were anything of the form a to the k where k was an integer. But k could be bigger than m, k could be negative, and so the question is that a to any one of those is also in this list or not. You use a trick, and in fact it's not a trick, it's a technique because we use it several times. At the end of this lecture, I'll use it one more time. You use the division algorithm. By the division algorithm, I can take this k, whatever it is, whether or not it's positive or negative, and divide it by m, and I'll get a quotient called q, and I get a remainder called r. That fact by itself is not really profound, but the thing that needs a proof is that you can always do that with r being a non-negative integer between 0 and m. Whenever you have k and divided by m, you have a quotient and a remainder is between 0 and m. This is possible because if the remainder was not in that range, then you didn't quite do the division right, and you could change the q to get there. If you look at a to the k, we now can write it as a to the qm plus r. And using the exponent rules, you can write as a to the m to q times a to the r. A to the m is identity because the m was the smallest positive integer that gave us identity. And e to the q is e, so I get a to the r. And so a to the k equals a to the r. And the point is that a to the r is in our short list because r is between 0 and m. That a to the k that walked through the dorm, we just showed that is one of the guys in our list. And so our list is all of g because every power of a is among these elements. And so we're done. Let's look at S5 and A equals 1, 3, 4, 2, 5. What's the cyclic subgroup generated by A? S5 itself is not cyclic, but this guy is cyclic. I just start with A, then A squared, and so on until I get identity. What's the smallest m with am equals e? And we can actually predict that because A consists of a 3 cycle and a 2 cycle. A is taking 1 to 3 to 4 to 1, and 2 goes to 5 and 5 goes to 2. 2 and 5 are switched. That's a 2 cycle or transposition. What happens when I take powers? If I do a squared, then 1 ends up going to 4. 4 goes to 3 and 3 goes to 1. 2 and 5 were switched. If you switch them again, you have identity. 2 is fixed and 5 is fixed. So a squared is going to be 1, 4, 3. And A cubed, the 3 cycle is going to become identity, but 2, 5, if you do the switch 3 times, 2 of them cancel each other out, but the third one stays, and so you're left with 2, 5. So every even power of A, so A squared, A to the 4th, A to the 6th, and so forth, for those 2 and 5 are fixed. On the other hand, every multiple of 3 power of A, so A to the 3k, then 1, 3, and 4 are fixed. When are all 5 elements fixed, which is what identity does, the first time that happens is 6, because multiples of 2 and multiples of 3 meet at 6. So the cyclic subgroup generated by A is A squared, A cubed, A to the 4th, A to the 5th, and A to the 6th, which is E. Inverses are among these already. A inverse is A to the 5th. The inverse of A squared is A to the 4th, and so forth. We're ready to define what the order of an element means. This is going to be a crucial concept. G is a group, and we have an element in the group. We look at the subgroup generated by that element, and we see how many elements it has, and that's the order of that element, order of A. So you look at subgroup generated by A, then you look at its size, and that number, the number of elements in the cyclic group generated by A, is called the order of A, and it's denoted by O of A. Note that we have used order in 2 different ways. We have order of a group, that's the number of elements in a group, and we have order of an element, which is the number of elements in the subgroup generated by that element. Equivalently, because of our previous theorem, we wouldn't have known this, wasn't it, for our previous theorem. To find the order of A, you start with A and just keep multiplying until you get identity. Order of A is the smallest positive integer D, such that A to the D is E. If no such D exists, then the order of A is infinity. It might be that the group is infinite. The theorem we proved was for finite cyclic groups. Even infinite groups have elements that have finite order, because one element might be generating a finite subgroup, but some elements might not. In any group, the identity always just generates the identity, and so the order of the identity is always 1. We're going to look at a bunch of examples and then one final useful theorem at the end. Integers with plus. This is an infinite group. Positive integers, negative integers, and 0 with addition. Identity is 0, and we use addition as our operation. The order of 1 is infinite, because 1 plus 1 plus 1 plus 1, no matter how many times you do that, you're never going to get the identity, which was 0. The order of 1 is infinite, as well as the order of everything other than 0. 0 being the identity, its order is 1. Another one of our favorite groups, D8, the dihedral group of order 8, generated by A and B. A is an element of order 4. B is an element of order 2. A is 90-degree rotation counterclockwise for a square, and B is a horizontal reflection. What's the group generated by A cubed? So you start with A cubed, you just keep multiplying it by itself. So A cubed squared, that's A cubed times A cubed, that's A to the 6th, that's A squared. For finding A cubed cubed, multiply A cubed squared, which was A squared, by A cubed, and you get A to the 5th, which is A. And then if you multiply that A again by A cubed, you get A to the 4th, which is E. You got everything. The group generated by A cubed is the same as subgroup generated by A. And so the order of A cubed, as well as order of A, is 4. AB, one of the reflections, when you multiply that by itself, you get identity right away. So the order of AB, as well as the order of all the other reflections, is 2. And so we can record the orders of elements of D8. There's 2 elements of order 4. Those are A and A cubed. Then we have 5 elements of order 2, A squared, the 180-degree rotation, as well as all the reflections, and identity has order 1. There's nothing of order 8, and that's because this group is not cyclic. These numbers are not, by the way, random, and you might be starting to guess what kinds of numbers could be orders. Let's look at Z mod 6Z with plus. This is a cyclic group, and we are going to use additive notation. So instead of A squared, I'm going to write 2A. And 3A instead of A cubed. What's the subgroup generated by 3? If you start with 3 and then add it to itself, you already get 0. 3 is not a generator for the whole group. And order of 3 is 2. On the other hand, if you start with 5 and add it to itself, you get 4. You do it one more time, you get 3. Another time, you get 2. Yet another time, you get 1. And finally, you get the identity 0. Remember, the identity is 0. It's easy enough to confuse 0 and 1. So the order of 5 is 6. 5 is an element of order 6. And because that's the same as the order of the group, that means that 5 is a generator for the group, and the group is cyclic. In fact, you can write down the orders of elements of Z mod 6Z. We have 2 generators, 1 and 5. This makes it very different than Z mod 5Z, which had 4 generators. Every non-zero element was a generator. But here we have 2 generators, 1 and 5, 2 elements of order 3, 2 and 4, and 1 element of order 2, and of course, identity, which is the only element of order 1 always. One final example before we prove a theorem. This time the group is GL23. So GL23 is the group of invertible 2 by 2 matrices with entries in Z mod 3Z. The entries are 0, 1, 2, and the group operation is matrix multiplication. But any addition and multiplications you do are going to be modulo 3. When you multiplying two matrices, you will have to multiply entries and add them. Those multiplication and additions are all done in Z mod 3Z. This is a group called the general linear group, and I have a whole video on the general linear group. And one element in this group is this matrix whose first row is 0, 1, and the second row is 1, 1. It's an invertible matrix. Its determinant is not 0. What's the group generated by it? And what's the order of this element? We look at powers of A. So A squared, A cubed, you can multiply these, and you will see that you will get identity finally when you find A to the 8th. And our theorem says that in a finite situation like GL23, all you have to do is start with A and just keep multiplying by itself, and eventually you're guaranteed to get E. The subgroup generated by A consists of A squared, A cubed, A to the 4th, A to the 5th, A to the 6th, A to the 7th, and A to the 8th, which is another name for E. And the order of this element in GL23 is 8. Now, GL23 is a group of order 48. It has 48 elements. Look at my video on general linear group to see why that is. And this subgroup generated by A is a cyclic subgroup of it of order 8. So inside this big group of order 48, that is not cyclic, but inside it is this cyclic subgroup of order 8. Final thing is a nice little proposition that's very helpful. And also the proof of it reminds you of the previous proof we did and is demonstrating a very useful technique. G is any group and you have an element in G. Assume that the order of X is M, some positive integer M, and say that you found some other integer S and X to the S was also E. If order of X is M, you know that X to the M is E. But let's say that X to the S was also E. Now M is a positive integer because orders are always positive integers, but S could be any integer. The claim of this theorem is that M divides S. So whatever S is a multiple of M. The only time X to the S is E is if S is a multiple of M. How would I prove that? The order is the smallest positive integer with X to the M is E. And we also know X to the S is E. We want to show that M divides S. How do we do that? Whenever we don't know if something divides something, a useful place to start is the division algorithm. We want to show that M divides S. So we take S and divide it by M. And the division algorithm tells me that I get a quotient and remainder. And the important thing is that R, the remainder, is a non-negative integer less than M. I want to show that R is really 0. If I show R is 0, then I've shown that S is a multiple of M and M divides S. So now let's use the stuff we know. We know that E is X to the S. That's actually the thing that we started out with. But instead of S, I can put QM plus R. And just like I had done in the previous proof, I can split this up. I can write it as X to the M to the Q times X to the R. And X to the M, I also know is E. And so I've got that X to the R is E. But what? Well, M was the smallest positive integer was X to the M is E. And R is smaller than M. What went wrong? Well, R can't be positive. And the only thing it could be is 0. And now I'm done. If you know that R is 0, then you know that S is QM. Therefore, you know S is a multiple of M. And you know M divides S. So whenever you have an element of the group, if you know its order, and if by luck you run into this other integer S and you know X to that is also E, then you know that thing is a multiple of M. This is the end of this lecture. Keep hydrated at all times. Like my video if you like it, and subscribe to my channel if you like to be subjected to math videos on your feed, and I will see you at the next lecture.